So, continuing on with our discussion on angular motion, let's now have a couple of examples. So, we have examples part 1. Sample problem number 1. You have a top. It spins with an initial speed of 1 radians per second. It makes 30 turns before coming to a stop. Determine the acceleration of the toy. So, the problem does not mention a particular direction. It doesn't mention if the object is spinning in the counterclockwise direction or if it's spinning in the clockwise direction. So, we are free to assume the direction of the motion. Assuming positive direction, why introduce negative sign if you don't have to? So assuming positive direction, the object is initially spinning with a speed of 1 radian per second in the positive direction. By convention, that's the counterclockwise direction. The initial velocity of the toy of the top is omega initial is equal to positive direction, positive 1 radians per second. Eventually, the top comes to a stop, so the final angular velocity is 0. The toy makes 30 turns before coming to a stop, so the total displacement is 30 turns, so theta is equal to 30 turns. 1 turn is 2 pi radians, so the total displacement is 60 pi radians. Now, this problem is an example of uniform angular acceleration, rather. There is acceleration. In fact, that's what the problem is asking for. Since the problem does not provide any equation describing the motion of the object, this is not a problem of non-uniform angular acceleration. This is uniform angular acceleration. And for uniform angular acceleration, you have 4 equations to choose from. One of those equations is omega final squared is equal to omega initial squared plus 2 alpha theta. We are looking for alpha, the acceleration, in this case, angular acceleration of the toy. We know the final angular velocity to be 0, so omega final squared is just equal to 0. We know omega initial, and we know theta. The only unknown is angular acceleration alpha. So isolating alpha and plotting in the known values, we are able to calculate the angular acceleration to be negative 2.653 times 10 to the negative 3 radians per second squared. Negative because from non-zero, the speed of the object becomes 0. The object was decelerating. Deceleration. The direction is opposite that of the motion. And since we have assumed that the direction was positive, that means the acceleration is negative, opposite that of the motion. So we have sample problem number 2. 2 rubber discs are touching each other as shown in the figure. You have disc A, radius of 0.5 meters. The pivot point is at the center of the disc. You have disc B, radius 0.1 meters. the pivot point of disk B is likewise at the center of the disk. Starting from rest, disk A begins to spin and accelerate at the rate of 0.25 radians per second squared. After 5 seconds, what is the angular speed of disk B? Starting from rest, disk A starts from rest, so initial speed, omega A initial is 0. The initial angular speed of A is 0. Since the two are in contact, if disk A moves, disk B will also move. In particular, if disk A moves in the positive direction, disk B will move in the negative direction, in the opposite direction. If disk A moves in the negative direction, clockwise direction, disk A will move in the positive direction, counterclockwise direction. So always, disk B will always move in the opposite direction as that of A because of the geometry of the situation. They are in contact as shown. Since disk A is at rest, disk B will also be at rest. So the initial speed of disk B, omega B initial, is also equal to 0. Disk A is accelerating at the rate of 0.25 radians per second squared. So the magnitude of the acceleration of A, angular acceleration of A, omega A, is equal to 0.25 radians per second squared. Time of travel is 5 seconds. Since the two are moving at the same time, they would have the same time of travel. So TA is equal to TB. Let that just be equal to T, 5 seconds. Radius of disk A, RA, is 0.5 meters. Radius of disk B, RB, is 0.1 meters. What is the angular speed of disk B after 5 seconds? So what is the final angular speed of disk B? Omega B final we are looking for. Now, disk A has an acceleration magnitude of 0.25 radians per second squared. It is constant at this value. Disk A is undergoing uniform angular acceleration. Since disk B is in contact with disk A, disk B will also be moving in uniform angular acceleration. But focusing on disk A is accelerating at the rate of 0.25 radians per second. No specific direction for the motion of disk A is provided by the problem. Since no direction is provided by the problem, we are free to assume the direction of the motion. There's no sense introducing negative sign into the analysis when we can avoid it. So let's choose positive direction. Let's assume that disk A is moving in the positive direction. It is spinning in the counterclockwise direction, which means B will be spinning in the opposite direction. It will be spinning in the clockwise direction. So A is counterclockwise direction, B is clockwise direction. A is undergoing uniform angular acceleration. So you have 4 equations to choose from. 4 equations of uniform angular acceleration to choose from by which to analyze the problem. One of those equations is omega A final is equal to omega A initial plus alpha A t. Omega A initial is 0, therefore 0 initial velocity for disk A. We know alpha A, 0.25 radians per second squared, and we know T, 5 seconds. We are able to calculate omega A final to be 1.25 radians per second. Now, going back to our basic definitions of velocity, angular velocity, omega is equal to d theta over dt. It is also equal to plus minus v over r, where v is the tangential speed. Plus minus refers to the direction of the angular velocity. Since A is moving in the positive direction, counterclockwise direction, omega A final is equal to positive VA final over RA. VA final, the final tangential speed of disk A as it spins or moves around the pivot point. In particular, the tangential speed of the edge of disk A. Converting this into scalar, just getting the magnitude of this equation, we have omega A final is equal to VA final over RA. Transferring RA to the other side, we have VA final is equal to omega A final times RA. Doing the same thing for disk B, omega is equal to plus minus V over R. That means omega B final is equal to negative VB final over RB. Negative because B is moving in the clockwise direction according to our assumption. And VB final is the tangential speed, final tangential speed of disk B, in particular, the tangential speed of the edge of disk B. Getting the magnitude of omega B final is just given by omega B final is equal to VB final over RB. No more negative sign because the negative sign pertains to the direction, and we're just talking about the magnitude of omega B final. Transferring RB to the other side, we have VB final is equal to omega B final RB. Now, for connected disks, geometry tells us that if the disks are connected as shown, the edges of the disks are connected as shown, the tangential speeds of the edges are equal, meaning VA final is equal to VB final, which gives us omega A final RA is equal to omega B final RB. Isolating omega B final, the final angular speed of disk B, we have omega A final RA divided by RB. Plotting in the values, kumpleto. The equation is complete. We are able to calculate the final angular speed of disk B. Omega B final is equal to 6.250 radians per second. And that's it for now. That's it for our discussion on the examples of angular kinematics. In the next video, we'll continue our discussion on angular motion. In the next video, we'll take a look at the concept of moment of inertia. So once again, that's it for now. Thank you for watching.